In this video, I'll demonstrate two ways to calculate the correlation coefficient, designated as an R. It is also referred to as Pearson's R and as the Pearson product moment correlation coefficient. In this data set, we have collected data about the production output from an assembly line based on the number of assemblers working on that line. We want to understand the relationship between the number of employees who assemble a subassembly and the number of subassemblies produced. The number of assemblers is considered to be the independent variable, and production is the dependent variable. We can quickly graph a scatter plot and look at the relationship. Often, graphing our data first is instructive about the type of test or analysis that is most appropriate. I'll select all of the data, then go to Insert and click on the Scatter Graph. It looks like as the number of assemblers increase, so does production. We would expect in that case to see some correlation between the two variables. Let me delete the graph. The first way to calculate correlation is in the Data Analysis menu. Go to Data, Data Analysis, and choose Correlation. My input range will be all of the cells. My data are grouped by columns rather than rows. I have selected the labels in the first row, so I've checked that, and we'll put the output in this Excel file. The correlation coefficient can be any number between -1 and 1. The 0.927 is our correlation coefficient between assemblers and production. A positive sign, which we have here, indicates that as one variable increases, so does the other, which is what we saw on the scatter plot. The closer our R is to 1, the more the two variables move in sync. Here, a correlation coefficient of 0.927 indicates a strong correlation. The second way to calculate correlation in Excel is to use the Correl function, equals Correl, and then it asks for the two arrays, which are my two columns of data. We can put the variables in any order. I'll enter production first, then assemblers, close parenthesis, and we get the same result as we did when we used the correlation function in the Data Analysis menu. This video has demonstrated two ways of computing the correlation coefficient in Excel. In this video, you'll learn how to run simple linear regression in Excel. This data set shows the inventory of diamonds and the price of each diamond for a jeweler. We believe there is a relationship between the size of the diamond and its price, and we'd like to be able to build a regression equation which would allow us to predict that price based on the size. Let's first plot the data to see if it shows a relationship. We'll put our independent variable size on the x-axis and the dependent variable, which we believe to be price, on the y in a scatter plot. So I will select the data in those two columns. Whichever variable is first, whichever column is first, will be treated as the x-axis variable. Click Insert and Scatter, and as you can see, we have a cluster around the origin, but we do show a relationship as the carat weight increases, so too does the price of the diamond. On the scatter plot, I can add a trend line by right-clicking and add trend line, and I can also display the equation on the chart. Let me make this equation a bit bigger so that we can see it more easily. This equation is what we will be able to get as our output from the regression analysis as well. Let's go ahead and run our regression analysis. I'll go to Data, Data Analysis, and select Regression from the list. In the Regression menu, my input Y range will be the dependent variable of price, and my x-axis is the independent variable. I'm going to allow the output to go on a new worksheet, and click OK. Multiple R is an indication of the correlation between our two variables. The number here will show between 0 and 1. When we have only two variables, this multiple r is the same absolute value as our correlation coefficient. However, it does not have a negative sign, so you cannot use this as an indicator of the direction of the relationship between the two variables. R squared is literally the r squared. It's also called the coefficient of determination. R squared measures the percent of variation in y that is explained by the variation in x. We can also say it is the percentage of the total variation explained by the regression equation. The higher the number, the more predictive power our equation has. What equation am I talking about? It is the same equation that we found on our scatter plot. I'm going to select this equation and copy it into the tab with our regression output. In a moment, we'll look at where the values in this equation come from in this regression output. The standard error is the standard error of estimate. The smaller this number, the more closely related our variables are. Now let's look at the Anova table. Our regression row is the variation explained by the independent variable. Residual is the leftover or unexplained variation, also called the error. We can derive the equation from the intercept and size coefficients column. The intercept is our y-intercept, the value at which the line crosses the y-axis. Size is our independent variable, represented by x, and the coefficient here is multiplied by that x, which is then added to the intercept to predict the price for that size diamond. For example, if we have a 1-carat diamond, we enter a 1 for the x variable, and our result is y equals $5,723.70. Now let's check our original data to see how close we came. In our original data, we have one 1-carat stone, which cost $4,868. You can see that our equation is not perfect. We do have some error. That's normal, but overall, a lot of the variation in price is explained by the size of the stone. In this video, I've demonstrated how to check the relationship between two variables using a scatter plot, how to use the regression tool in Excel's data analysis menu to run a simple linear regression, and build a regression equation from the results. This video will demonstrate how to transform a variable into its base 10 log. In this dataset, we have the top 60 golfers from the 2013 PGA Masters Tournament, and the prize money each received. We like to study the relationship between score and prize. Let's begin by graphing the two variables on a scatter plot to look at the relationship. I would consider score as the independent variable, and prize as the dependent. We'll select the score and prize columns. Whichever variable is in the first column will be treated as the x or independent variable. Insert scatter plot, and as you can see, a curvilinear relationship is revealed. As score increases, prize money decreases at a decreasing rate. Because we need a linear relationship in order to run a linear regression, one common method to be able to create that linear relationship is to transform a variable by taking its base 10 log. I'm going to create a log prize column and take the log of the prize variable. As you can see, there are multiple log formulas in Excel. If we just selected the first one, it would actually allow us to specify the base of our log, but we want log 10. And Excel offers that as an option already, so we'll select that one. I'm going to close parenthesis, and here is the log. I can drag that all the way down the column by double-clicking in the bottom right corner of that cell, and I filled in my column. Now I'll run another scatter plot and we can compare the two. I'll take the score and the log prize, insert scatter, and as you can see, this relationship is much more of a linear relationship. There is still a slight curve, but let's run the regression and see what it tells us. I'll go to Data, Data Analysis, and Regression. In my input Y range, I want to take the log variable. It's important that our column header reflect that this variable has been log transformed, and I'm going to include labels so that we keep track of what we used as our independent and dependent variables. We'll have the output in a new worksheet, and let's take a look. Our multiple R indicates that we have a strong correlation between the two variables of score and log prize. Our R square of 0.94 indicates that 94.7% of the variation in Y is explained by the variation in X. Notice that our correlation relationship in this case is negative. As score increases, prize money decreases. However, multiple R does not indicate the direction of that relationship. We can confirm that for ourselves by equal Correl, and we'll go back to the original data and take score and log prize, and we see that the relationship is negative. The numbers match, but the sign is not included in the multiple R. Our correlation is negative between the variables. The regression equation is Y log prize equals intercept plus score of coefficient times X. Let's predict the outcome with a score of 290. Y equals 5.3396. Remember, this is the log base 10 of the prize money. We have to take the anti-log to see the result in dollars. We enter equals 10, and we raise it to the power of the log value, 5.3396, and we get 218,575, which is the dollar amount of the prize money. Now let's see how we did. We don't have a score of 290. We have a 289 and 291, but we can see that the value we predicted lies in between those two scores. In this video, we have demonstrated how to log transform the dependent variable when the relationship is curvilinear, then run regression on the resulting independent and log transformed dependent variables.